We're going to do a change in slope. So this is going to end up being a hydraulic jump. On any of these kind of problems, what the first thing we want to do is we want to figure out what normal depth is going to be, because that's going to tell us if this was a really long channel, how deep the water would be. And then we need to find out what critical depth is, and that's just going to kind of give us a point of reference. So let's do that. So let's open up the Excel spreadsheet. We're going to put in all of this information. First thing we want to do is just make sure that we're in the right system of units. So, we're going to do this problem in English units. So that means we're going to use English gravity. We're going to use this English unit correction. We want to change the bottom width to 8. That's the width. This is a rectangular channel. We don't know the depth, so we're going to figure that out. We'll just leave that one. This is a rectangular channel, and so for that, we're going to set the side slope, this thing M here. We'll set that to 0. And because there's two slopes, we're going to do this a couple of times. So for the first slope, we've got a bottom slope of 0.008, Manning's roughness of 0.013, and a flow rate of 200 CFS. So let's get normal depth first. So what we want to do is we want to set the Manning flow rate to equal the 200 that we're into. So this would tell us, basically we're going to find out what the depth would be in this channel if we had 200 CFS going down it for a really long distance. To do that, we'll goal seek. We're going to set this cell here equal to 200 by changing the depth. 2.01, Froude number of 1.47. So this is a supercritical or a steep slope. We're going to need to get the energy, and we're also, because there's going to be a hydraulic jump, we're going to need to get the specific force. So let's go in and write that down. So to help us work the problem, let's call this section A. And so that's going to be, A is going to be associated with the slope of 0.008 and B with the slope of 0.0004. So for section A and section B, we're going to do this. So we need to know what normal depth is going to be. So for section A, that's 2.01 feet. The Froude number, we won't need to work the problem, but let's write it down. It's going to remind us that it's a steep slope, supercritical. The specific force, I'm going to call it momentum, is 93.4. And let's find out what's going on in the downstream section next. So we'll have all the same information, but we're going to change the bottom slope. And so at this depth, with this bottom slope, we're not getting nearly the flow rate that we need, so this depth is going to be deeper. That means the velocity is going to go down. Let's see what that is going to be. So we're going to goal seek again. .07, and the Froude number is less than 1, so let's call it 0.3. And the specific force is 172. So let's write that down. So this is if we had a really long section of channel with this really, it's a mild slope. This is what the depth of the water would be. Okay. And then the last thing that we need to do is we need to get critical depth. So we want the Froude number to be equal to 1 to get critical depth, so we'll goal seek that one again to 1. By changing the depth, we get 2.69. So let's sketch this out. Okay, so what that means, because we've got a supercritical channel upstream and a mild channel or a subcritical channel downstream, for the subcritical section, downstream controls. And so water's working its way from this point of interest upstream, and so the control direction is that direction on the subcritical side. And so we could actually write in that we know if we go far enough downstream that we are going to be at uniform depth. And the same thing is true on the upstream section. So for section A, the water's racing down the channel, it's going supercritical. And so if we go far enough upstream, we'll also be at uniform depth. And so then the question is, what happens in between? So A is upstream controls, B is downstream controls, and those two control directions are going to intersect. And when that happens, we'll have to have a hydraulic jump. And so what we need to do is we need to figure out, does the jump happen upstream of the change in slope, or does it happen downstream of the change in slope? Because that's going to tell us whether we have an S3 curve, or sorry, an S1 curve or an M3 curve. And so the only way to really do that is to look at what would happen if there was a way to force the hydraulic jump to occur right at the change in slope. And so then what we'll do is we'll compare. If we could make the hydraulic jump happen at the change in slope, then what would happen is on both sides of the jump, it would be normal depth. And that's a weird thing. It's never going to really happen that way. But it turns out that hydraulic jump is always, or usually, going to jump to normal depth on one side or the other. And I'll show you how that works. It'll make more sense after we see this example and then the next example. But for now, let's just say one way to identify whether the jump is upstream or downstream is to compare the momentums at the two cases, and whichever one has the highest specific force will win, and in other words, push the hydraulic jump away from that point. So if we look at the specific force for the normal depth here, which we're presenting as being possibly at this location, that specific force is 172. That's a higher specific force than the normal depth upstream, which we're presenting as possibly happening at that point. So if there was a way to force the water to flow through uniform conditions all the way to some jump that would happen right at this location, and also in the other direction, then the specific force up here is actually greater, and it would force the hydraulic jump to move this direction. And so what that means is that the jump is upstream. And so we can actually sketch this out now. Let's write it out too, so that we can see that. So we've got uniform conditions, to our change in slope. And then we have an S1 curve until we get to the hydraulic jump. And then there will be a jump. And it'll be uniform conditions to that point too. And so let's write that in our notes. So we're going to compare the momentum or specific force at section A and B. Oops. So, well, some of the things that we are interested in is how far is this jump upstream of that change in slope? So what is this dimension? We'll call that thing delta x. So we're going to do that calculation. To do that calculation, we need to know what that depth is. And so that depth, it turns out, is the conjugate depth of our uniform depth, right? So this is all the same depth here, and the specific forces on either side of a hydraulic jump are the same. That's the rule. That's how it works. And so we want to take a look at that. So if we make a plot of depth versus momentum, or specific force, we'll get a plot that looks like that, with critical being right here. And we need to demarcate this location. So let's call this location J. So basically what we're saying is that here's the specific force for normal depth in section B. That's 172. Here's the specific force for momentum in the upstream section. That's section A. That's 93, and this is the thing that we're interested in. And that location, that's the depth of the jump. Okay, so let's do that calculation. So we need to go into Excel and we need to goal seek for that y sub j, the subcritical depth that corresponds with 93.4. Those are called conjugate depths. So the way that goal-seek works in Excel is that it guesses a value of y, and it sees if we're closer or farther away from our answer, the thing that we're looking for. So we want to make sure that our first guess is along the subcritical portion of this chart. So we need to have a guess that's up here somewhere, and it will converge on the answer that we're looking for. If we guessed a supercritical depth, it would converge on this normal depth answer for A. So let's check that out. So I'm just going to put in a really high number. For depth, that ensures that we've got a subcritical depth. We could also just look at the Froude number and get that right. So we're going to goal seek. We're going to set the specific force to 93.4 by changing the depth. And I got 3.5. We're going to need to write down this energy also. So here's the energy, 4.29. And to do the delta x calculation, we're also going to need to write down the velocity, 7.14, and the wetted perimeter, 15, the hydraulic radius. And I've got this built into my spreadsheet. So what I'm going to do is I'm going to copy and paste this. I can't remember. We want to make sure when we're copying and pasting that we're going to paste values. The values are the ones that we just want the numbers in there, not the equations. All right. So now I can go back up and I can change the depth. And these stay the same. That's our intent. Okay, so let's write that down. So our delta x calculation is going to take place along this green line. So we also are going to need that same hydraulic radius velocity information at this point. And so I think it might be maybe better to go ahead and put in another identifier for that. So let's call this section K. Now all the properties at K are the same thing. That's normal depth for the downstream condition, but I just want to make it very explicit. So let's write down information for section J. So we just found J. That depth was 3.5 feet, and the energy at J was 4.29 feet. We need to know the velocity, 7.14, and we need to know the hydraulic radius, 2.14. So we also need to get that information for section K, which is normal depth for the section downstream. So we need to go back to our spreadsheet to get that information. So we're going to solve for normal conditions downstream. So we've got this bottom slope in, and we're going to goal seek that to 200. So we've already done this once. And now what I'm going to do is I'm going to go ahead and copy this information into the second part. And we still haven't fixed this. So these are the two parts that we need, but we know that the hydraulic jump is going to happen upstream. And this delta x calculation is actually referencing the slope here. So I need to go ahead and to get the right answer in my spreadsheet, I need to change this slope. I'm going to change that to 0.008. And now I've got 286 feet upstream of the change in slope. That's the right answer. I'm going to show you how to do that by hand next. So to do that, we need to go ahead and plug in all the information for section K. Oh, that's right. That's right. And then we also need to get the average values of velocity and hydraulic radius. So the average value is 5.63 for velocity and 2.14. I see that I made a mistake here. I wrote down the wrong hydraulic radius for section J, so I'm going to get a little typo here. Oh, maybe I won't be able to erase that loop. I'm going to scratch it out. We'll write the right number in. Okay. So now we need to get the average slope of friction. That's the rearrangement of the Manning equation. Let's write that equation down real quick. So the average slope of friction the Manning's n times the average velocity over our unit correction, 1.49 times the average hydraulic radius to the 2/3 power, and then that whole thing gets squared. So if we put our numbers in, oops. So there's a way to kind of do the smell test on this slope of friction. It should be greater than this value because the water's moving faster through that section on average than it is downstream. So we're comparing what's going on between these two with what's going on downstream in section B. And it should be less than the upstream section, where the upstream section is moving quite a bit faster. So there's kind of a smell test, and so this is a reasonable answer. Now we need to do our delta x calculation. So the delta x has us going from the energy of the downstream section minus the energy of the upstream section over the bottom slope minus the slope of friction. So that means we're going to use E sub k minus E sub j divided by S naught and SF bar. Now if we get these two mixed up, we'll get a negative answer. And if you get a negative answer, then you're probably doing something wrong, or at least you should expect the negative answer if that's what you're going to get. So if you get a negative answer by mistake, you need to go back and make sure that you're doing the delta x calculation correctly. So there's our answer for delta x. And so we can actually draw this water surface profile. We might not get the exact shape of this part of the curve right unless we chose some more intermediate values of depth between 3.5 and 6.07. But we could. So we could choose 3 or 4 more depths between those two, do the delta x calculation, and that would tell us what this shape is going to be. So this is a first example, but we're going to do the next example and change the downstream slope, which will end up moving the hydraulic jump downstream. So this is the same upstream slope, but it's got a different downstream slope. So we'll get to reuse some of the info from the last example, but we do need to figure out what's going on downstream. Let's go ahead and we'll call this section A again. This will be section B again. So we've got all the information for section A, but we need to get the info for section B. Let's go to the spreadsheet. So we need to find out what the downstream normal depth is going to be. So let's put that bottom slope in. And so we're going to goal seek this thing, the Manning's flow rate, so that we get 200 CFS. Oops. Did something wrong there. Okay, 3.29 is the answer. We got our Froude number, it's less than 1. We're going to need to know what the specific force is because there's going to be a hydraulic jump. So we'll compare this specific force with specific force from section A, which we already know to be 93. And so we can see that this specific force is less. That means that there's going to be a hydraulic jump downstream. We'll get back to that. Let's write all that down. So for section A, we did this once already in the previous example. 2.01. The specific force was 93.4. Section B, normal depth 3.29. Froude number 0.74, specific force 90.49. And we can sketch this again. I skipped the critical depth. That was 2.69. Let's write that. So we can sketch that in there. Critical depth or normal depth upstream, supercritical, critical depth normal depth downstream, subcritical, and so if we go far enough upstream, we'll have uniform depth. And if we go far enough downstream, we'll have uniform depth. But the interesting question is what's going on between them two. And we know that there has to be a hydraulic jump because the upstream controls and downstream controls conflict at the hydraulic jump. So the way to figure out, is this jump upstream or downstream of the change in slope, is to compare the depths, or sorry, the specific forces if the jump were to happen right at the change in slope. Or another way to think about it would be to say, let's compare the specific forces for normal depth for the upstream section and for the downstream section. So we did that once already. Hopefully it makes a little bit more sense now, but we're going to do it again. So in this case, the specific force for section A is greater than the specific force for section B, and that means that the jump is downstream of the change in slope. And so we can actually draw that out now because we compared these two numbers. So we've got uniform depth to this point, and then we're still supercritical, and we know that we're going to be supercritical on this side now, so that makes this an M3 curve. Not sure I labeled it last time. M3 curve to a hydraulic jump, and the jump goes straight to uniform depth. We didn't talk about it as much last time, but if you consider this is the geometry that's happening, downstream controls, and so as you work your way upstream, there's nothing that would cause the depth of the water to change, and so it's going to remain uniform depth right up until the point that it gets to the jump, and then it'll jump to the conjugate depth of this specific location. So there's the conjugate depth. So these two are conjugate depths of each other, and on either side of a hydraulic jump, it's always the conjugate depth. And so what we need to do is we need to find the conjugate depth of y normal downstream. We need to find this conjugate depth. So let me sketch that out again. So if we draw out the specific force diagram, looks like this. So here's the specific force for section A, 93. Here's the specific force for section B, here's the normal depth for section B, so this is 3.29, and so that makes this depth, that's the conjugate depth. This is the thing I'm going to call this y sub j. So let's label this section right here. That'll be section J. And so we need to find that out. So we need to find out the conjugate depth of 3.29. Let's go to the spreadsheet. So we want to put in a supercritical depth. We're looking for a supercritical depth. So we got to put in a first guess that's supercritical. Here's 1. We want to check to make sure that Froude number is greater than 1. So let's go goal seek the specific force. So 2.16 is the answer. That's going to be one side of our delta x calculation. So I'm going to go ahead and nab those values and paste them in right here for our calculation. You can see how much easier this is than doing it by hand. So I've got those values. Remember, we're going to do this by hand. So to do it by hand, we need to know this velocity, and we need to know this hydraulic radius. So we're going to write those down here in a second. For now, I want to go ahead and do the delta x calculation. So I'm going to go ahead and find normal depth for our upstream section again. I mean, I could actually shortcut this. Let's just do that. I know the answer is 2.01, and so I can take these values now, paste them in there, and then I want to check to make sure that the bottom slope that's up here is the slope that corresponds with where our delta x calculation is taking place, and it is. So we can check and see I get 34. Okay, and that might change a little bit. If I had goal seeked this number, you can see we're a little bit off. There's some rounding that happens in the goal seek. So let's write that info down. So our delta x calculation is happening from here to here. And so let's ID this change in slope as a point of interest. I called it K last time. I'll call it K again. So this is where the delta x calculation starts, and J is where it stops. Previously, J was where it started and K is where it stopped. So that things have moved around a little bit. You just want to make sure you keep upstream and downstream in order. Okay, so we need to know information about section K, which is the same thing as the normal depth for upstream. And then we need to know something about section J. So what do we need? We can write down the depths. That's 2.01 and 2.16. We need to know the energies. 4.41 and 4.24. We need to know the velocities. And the average values. So if we average the velocities, we get 11.99. And then we need the hydraulic radius, radii. And the averages. So if we do our SF bar calculation, the average slope of friction between those two, this is our unit correction. We get 0.0072. So again, we can use this value. We can smell test this value. That number should be less than the upstream slope because we know the water's slowing down through this M3 curve that we're interested in. And it should be greater than the bottom slope in the downstream section because it's not going that slow. It's not going as slow as the downstream section. So this smells right. Let's go ahead and do our delta X calculation. And when I did it in the example, I got 32 feet. In the spreadsheet, we got 34 feet, so that's probably a rounding difference, but that's the answer. So we should talk a little bit about energy since we didn't do a step or something that would require us to use our energy balance approaches. This is a type of energy balance, but I wanted to go through it real quick so that we have something to talk about. So if you think about the water moving from left to right, so if we start upstream, the energy is the same all throughout this section, and that energy is 4.41. At that point, the energy loss is greater than the energy gained as it moves downstream, and so the water has to slow down. It's going to lose energy, and so basically this M3 curve corresponds with this section. So the water is basically burning off energy, and so this jagged line is moving from 4.41 to 4.24. That's this section right here. Once it gets to that point, then the hydraulic jump happens, and there's also energy loss inside the hydraulic jump, and so then we get energy loss through this section until we jump directly to normal depth, which is this point. So this hydraulic jump is also energy loss. And then at that point, the water's moving downstream and it's gaining the same amount of energy as it is losing due to friction. So this is an example of two different momentum balance problems or hydraulic jump questions, and then also a little bit of a discussion about the water surface profile for an M3 curve. And you could do the same thing for the S1 curve that we saw in the first example.